So now we're going to look at the topic of functional completeness. Now this is one of my favorite topics to cover when we do this course. It's kind of mind-blowing at certain points. So the idea is a set of connectives like not, or, and. A set of connectives is functionally complete when you can use the connectives in that set to define all possible connectives. So the idea is that if you've got a functionally complete set of connectives, you don't actually need any others in some sense, because you can define any other connective you want using the ones in that set. So this idea of defining a connective in terms of others, we've almost seen that. I mean, we've talked about how a biconditional is equivalent to the conjunction of two conditionals, one going one way, the other going the other way. If you do the truth table for this thing, you'll see that it turns out the same as the definition of double arrow, the truth table definition of double arrow. So this fact about equivalence, that these two forms must always, instances of these two forms must always have the same truth value, that kind of gives rise to a fact about definability here. What we see is that we don't really need double arrow in our language. We can define it in terms of arrow and conjunction. So you don't really need that. Whenever you wanted to write that, you could instead just write this thing. Or you could let yourself write it, but then regard it as an abbreviation of what you would get if you expanded out what you've written according to this definition. Okay, so that's what I mean by defining a connective in terms of others. And now by all possible connectives, well, I don't just mean one-place connectives like not, and two-place connectives like arrow and disjunction and so on. You can also have three-place connectives. Like if I use the hash symbol as some new connective, well, I can say it takes three inputs, alpha, beta, and gamma. And I could define it using a truth table. Now this truth table, because there are three possibilities and two truth values, it's 2 to the 3. It's 8 possible combinations we have here. So the definition of hash will be a column of length 8. And then if I fill in that column with T's and F's, I've got a perfectly good three-place connective. So because it's a column of length 8 that we use to define it, and there are two truth values, well, there are 2 to the 8. There are 256 different ways of filling in that column. So that's how many possible three-place connectives there are. And this number increases very quickly with the number of places. So a 4-place connective, you need a column of length 16 to define it. And well, there are more than 65,000 ways to fill in such a column. So there are many, many more possible 4-place connectives. But all of these can be defined using the connectives in a functionally complete set. And as we'll see, there are some very compact functionally complete sets. Okay, so that's all possible connectives. So what I really mean is all possible truth functional connectives, meaning the kind of thing you can define in a truth table. So for example, we're excluding things like the word because in English, at least sometimes, plays this syntactic role of taking sentences on either side and forming a larger sentence. But we're excluding that from consideration. There's no hope of defining because using a truth table. If you think about it, take a true, I mean, it depends on more than just the truth values on either side, what you get here. So take a true because statement like this. The light is on because I hit the switch. If I replace that I hit the switch with a different true sentence, like snow is white, it's no longer true, right? So that shows that because, so for example, the light is on because snow is white. Snow is white is also true, just like I hit the switch is true, but that because statement is false. So because statements are not truth functional. But when I talk about all possible connectives here, I mean truth functional ones. The ones where the truth value of the whole is a function of the truth values of the parts. The kind of connective you can define with a truth table. Okay, so we're going to see now that, in fact, our familiar set of connectives that we have in propositional logic is functionally complete. And the way we're going to see that to be, the way we're going to see that to be true is we're going to look at a method which lets you define any possible connective using the connectives in that set. And this method is called the truth table row description method, for reasons we'll see. And in fact, this method, so the idea is it works with some connectives and lets you define any others using them. And in fact, it only utilizes these three connectives. So what we're actually proving is that this set is functionally complete. And so of course this set is. We've just got extra stuff in that one. Okay, so I'm going to illustrate how this method works. And the point is that the method works generally no matter what the example is. And the fact that the method exists and works generally is what proves this claim, this functional completeness claim. So I'm just going to look at an arbitrary connective. I'm going to use a two-place connective just for time reasons, but again, it works with any number of places. So we set up our truth table, and I'm just going to randomly, I'm going to make it TF. So that's not one of our familiar ones. I don't know of any common symbol for that one, but it's a perfectly good connective. And now let's use this method to get a definition of it that just uses negation, disjunction, and conjunction. Okay, so the first step, it's a two-step process to get this definition. First step is to describe the rows where this connective, which I've labeled question mark, just to emphasize it could be anything. Well, when does question mark give us back true? And we describe those cases. So we describe the T rows. So let's do that step. So here it's true on this row. And so we just describe what's going on there. We say, well, there alpha is true and beta is also true. And this thing, this conjunction alpha and beta, well, it's true on this row, only this row. It's true exactly on that row and false on the others. Okay. And now that's that T row described. Here's the other one. For this case, there's one other one, and that's where alpha's false and beta's true. So here's where negation comes in. To say that alpha's false, I can say, well, not alpha, and, well, beta's true, so I just write beta. So this thing, that just uniquely describes that third row. It's true just on that row. That's step one complete. Now step two is you take the disjunction of those descriptions. So I'll just say disjoin the descriptions. So I take the disjunction of those conjunctions, and that will serve as my definition of question mark. Okay, so that is truth functionally equivalent to that. And I mean, you can see that pretty quickly because I mean, this disjunct is true exactly on this row. This one's true exactly on this row. And on these other rows, both disjuncts are false. So you can do that in more detail, more slowly as an exercise, but there you go. That's proof that the definition works. We don't really need question mark when we have these three, because we've got this definition we can use. And now the point is, so you can think of this as saying it's a disjunction of the different ways that this kind of statement could be true. So again, if you think of a statement as in effect saying that its truth conditions are fulfilled, it's like saying, well, either I'm true in this way or I'm true in that way. And that's sort of the two ways that I can be true. So, and again, this definition works in no matter what question mark is, except now just a couple of caveats. There are two special cases, but they're very easily dealt with. So you might want to think about, well, one of the special cases, so I mean cases where you don't, if you apply this method, you don't get a disjunction of conjunctions. And so there are two such special cases. One case is where you only have one T row. Well, then you've got the row description, but then what about step 2? Well, you just skip it. That's the way you handle that case. So in the case where a connective is true on just one row, or gives back true on just one row, then its definition will just be a conjunction, just the description of that row. So that's sort of easier than the normal case. The other special case is there are no T rows. It's F's all the way down. Well, the solution there is you just pick some arbitrary contradiction that you can write using these connectives. So alpha and not alpha is a natural choice. That thing is just false on all rows, so it will serve as the definition of a connective that gives you back false no matter what. And you might think, well, it's weird, why is there only alpha there? What if it's like a 3-place connective? What happened to beta and gamma? But if a connective just gives out false no matter what, you can think of it as sort of ignoring its inputs. So that's why just any old contradiction will do for that special case. So apart from those cases, what you get is a disjunction of conjunctions to serve as your definition. It won't generally be the most compact definition available, but it will always work. And so the fact that that method's there and always works, that proves this claim. So we've now proven that. Okay, so now let's just push this a little bit further. Okay, so we've proven that and therefore this using the row description method. Now there's still some redundancy here. So if you've got negation and conjunction, you can define disjunction using them, meaning that this set is functionally complete. Likewise, if you've got negation and disjunction, you can define conjunction. And so the reason for that, it's these things called the De Morgan laws. So that's after a 19th century logician, Augustus De Morgan. So it's this pair of laws relating disjunction to conjunction. So the one I like to think about, which I find more intuitive, is that alpha disjunction beta is equivalent to this. This is a definition of OR using not and. So I mean, you can think of a disjunction, if you think of it as saying that it's true, right? A disjunction is only false, it's an inclusive disjunction, remember? So it's only false when both sides are false. So you can treat it as just in effect saying that that's not the case. It's not the case that both my sides are false. That's tantamount to that being true. And that's what this says explicitly. So if you do the truth table, you see this thing will serve as a definition of disjunction. And it's the same thing the other way around. You can just switch conjunction and disjunction. Okay, so because you can use, for example, these two to recover disjunction, now we know this set's functionally complete by the De Morgan laws plus the row description method, which gets you everything once you have those three. So that's pretty cool, but we can actually go even further. Now it's not that there's any redundancy in these sets. You can't just delete not, for example, and still have a functionally complete set of connectives. You might want to have a think, for example, why can't you define all connectives using just and? You can see why with a bit of thought, but so it's not as if we can eliminate one of those and just leave the other one in one of these sets. But there are other connectives. There are two, and each of them is functionally complete all by itself. And given what we've already established, the way we're going to show that is to show that using one of these you can define negation and you can define conjunction. We can do the same with disjunction. We'll show that from one of these you can get back both of these, and then what we've already seen establishes that this is functionally complete. So the one we'll look at in more detail is sometimes called NOR, also sometimes called the Peirce arrow, after Charles Sanders Peirce, a great American logician and philosopher and kind of scientist who made this discovery, in fact, that both of these are functionally complete, around 1880. But this didn't catch on. This isn't something he published and made known to a lot of people. And so it was, these facts were independently discovered by Scheffer in around 1913. And that's actually how people, how this became widely known. So Peirce, yeah, he didn't manage to publish it. He had a bit of a rough trot. He only worked as, he was only able to do this stuff professionally for a few years, and then things went pear-shaped for him. And before that, for a long time, he was employed, and I think while he was an academic, he was employed on the US Coastal Survey. Was sort of his main career, was doing this work towards having more accurate maps of the US coastline, and he just did a lot of this stuff in his spare time. But in fact, both people discovered both of these facts, both connectives being functionally complete. But for whatever reason, this one bears Peirce's name, and this one is sometimes called the Scheffer stroke, after Scheffer. And it is also sometimes called NAND, for not and. You can think of it as saying it's not the case that both my sides are true. So to give the definitions, this NOR one, it's just true in that case. And this NAND one, well, it's false only here when both sides are true, and it's true otherwise. Now, so they both are functionally complete, but I'm just going to focus on this one, and we'll show that the Peirce arrow, NOR, can be used to define all other connectives. And the way we're going to do it is we're going to define negation, and then we're going to define conjunction using this arrow. So let's start with negation. So I mean, there's something a bit funny about this. You might wonder, like, negation's a one-place connective, so how can we define it using a two-place connective? Well, the trick is you just repeat the input. So alpha arrow alpha is equivalent to the negation of alpha. So if we just compute it to verify this definition, well, when you've got alpha true, then you've got true on both sides. And that's when, and in that case, NOR gives us back false. Oops. And on the second row, well, alpha's false. And so we've got false on both sides, and that's the one time that NOR gives us back the value true. So there we go. That is a definition of negation. If you've got Peirce's arrow lying around in your language, if you want to negate something, you can just write it twice and put the arrow in the middle, and that will achieve the same effect. So now let's look at, I'll use this table. Let's see a definition of, what I'm going to do is a conjunction in terms of the arrow. Okay, so this thing, now this is not super intuitive, to me at least, but if we just sort of turn the crank and do the calculation, we'll see that this whole thing is equivalent to alpha conjunction beta. Okay, so top row, well, true arrow true gives us false, and that's what we have here too. So overall, we've got false arrow false, giving us true. Now in this case, alpha's true and beta's false. So overall, we've got false arrow true, giving us back false. Very similar story for the third row. Fourth row I'll leave as an exercise. And so we see that this thing turns out exactly the same as the the truth table definition of conjunction. So that means you can define conjunction using this thing. So let's step back and see what we've shown. We've got, using this arrow, we can define negation and conjunction. So we know that we can define this set using just the arrow. And we know that that set's functionally complete by the De Morgan laws and the row description method. So I won't show you definitions involving NAND. Maybe that could be an exercise, or you can look them up. But this is pretty cool, I reckon. It's quite surprising in a way that you can just get by with one connective like this. And in a way, this is just a very general fact about sort of the space of functions on two elements, truth and falsity. Like, it's kind of an accident that humans discovered this by thinking about logic, like truth and propositions. You know, it happened that way, and it could have happened a different way, like thinking about electronic circuit design or something like that.